Okay, good evening, everyone. Let's wait for a few minutes, then we'll start. Okay, so the first problem is we have some dispersion relation for a one-dimensional monoatomic crystal with lattice spacing A, and the dispersion is given by omega equal to A sine mod of sine k by 2. So we need to find the group velocity at the boundary of the first building zone. So yeah, so let's try to find and then I will solve. এখন চলা না স্লো হয়ে যাবে So anyone found the answer? Okay, so let me solve it. So we have given the dispersion relation like this. So a mod of sine k by 2, and now let's focus on when mod of sine k by 2 is greater than 0. So then group velocity Vg is given by the formula d omega dk, right? So it is cos k by, sorry, mod of cos k by 2 and then a by 2. Now we need to find this at the boundary of first Boolean zone. So if it is on dimensional array, so if this is 0, then plus pi by a and minus pi by a. This is the first Boolean zone. Now boundary is this one, plus pi by a and minus pi by a. So Vg at k equal to pi by a or minus pi by a, this will be, in both the cases plus or minus, it comes cos pi by 2, which is 0. So at the boundary of the first Boolean zone, the group velocity is 0. And this can also be seen from the dispersion relation itself. So if I draw the dispersion against k, then it will be, let's say these are boundary, pi by a minus pi by a. So mod of sine k by 2 will look something like this. And similarly symmetric, there will be symmetry in minus part as well. But the main point is this is at the first Boolean zone, at the corner of the first Boolean zone, minus pi by a and plus pi by a. This is parallel to the x-axis, that is k-axis, right? So then the slope is basically 0. Slope is 0, and group velocity, which is d omega dk, actually determines the slope. Okay, so that's why it is also 0, and it is also at 0 at k equal to 0. Okay. So next problem, So consider a metal which obeys, obeys the Sommerfeld model exactly. Now, if EF is the Fermi energy for the metal at T equal to 0 Kelvin, and RH is the Hall coefficient. So, what is Hall coefficient we discussed in last session. So now we need to find the relation between Hall coefficient and the Fermi energy, and we assume that this is a 3D system. So Fermi energy relation we know, right? To solve this problem, so if you forgot the Hall coefficient was 1 by n into E. E was the electronic charge, or in general we can write it like n into q. Q is the charge and n is the number density of charge. So anyone found the answer? It will be the correct option. This is a fairly easy problem. So n is carrier concentration or the number density. Now Fermi energy for a 3D metal is given by this. We have done a lot of problems on this Fermi energy relation. So here n is again the carrier concentration. So RH equal to 1 by, or let's say RH is proportional to 1 by n. Now so from this relation EF to the power 3 by 2 will be proportional to n, right? So if we use this one, then this will be f to the power 3 by 2. So RH is proportional to f to the power minus 3 by 2. So option C is correct. Third problem. So the dispersion relation for electrons in a conduction band for a semiconductor is given by this, where alpha and E0 are constants. Now, if omega c is the cyclotron frequency for the electrons in a magnetic field B, then we need to find the value of alpha. So, I think you guys know what is cyclotron frequency. So, whenever a magnetic field is applied, let's say in xy plane, the electrons is there, and we have applied a magnetic field along the z direction. Okay, so the electrons will perform cyclic motions. Okay, due to the Lorentz force. So what is Lorentz force? V cross B. So B is along this direction. Let's say V initially remains this direction, then V cross B will be along this direction in the xy plane itself. So it will perform an circular motion. And the frequency of that circular motion is called the cyclotron frequency, and it is given by EB by m star, where m star is the effective mass that we have studied in band theory of solid. Okay, so we need to find omega c, or sorry, the value of alpha. So if omega c is the cyclotron frequency, and we have energy as a function of, so E0 plus alpha k square. So from this we can get m star, right? So if we put this m star in this equation, then from this equation we have to extract alpha equal to what? And the formula for m star is h square by d2e dk2. So let's try to find out. Okay, that's right. Option D is correct answer. So let me solve it. So what will be m star? Okay, so dk will be alpha 2 alpha k, right? And then d2e dk2 will be 2 alpha. So m star is h square by 2 alpha, and omega c is given by eb by m star. So eb by h square into 2 alpha, and we need to find alpha. So alpha will be h bar square omega c by 2eb, which is this option. So next problem. So there are two questions. Uh, Based on the following density of copper, resistivity is also given, and then atomic weight. So we need to calculate number one mobility and then average time between the collisions, which is basically tau. We usually denote. So there is no option. So find the answer and let me know in the chat box. So anyone found any of this quantity, mobility or average time between the collisions? So so you guys understand the problem, right? Okay, so let's solve. So we have given density, resistivity, and then atomic weight, right? So first of all, resistivity is inverse of the conductivity. So rho is the resistivity, and this is conductivity. And in classical Drude model, conductivity is given by n e squared tau by m, where n is again the carrier concentration. Tau is the time between the collisions, and m is electronic mass if it is the charge carrier is electron, and e is the electronic charge. So we need to first so what we necessarily know is that sigma value we know. because sigma means 1 by rho, so 1 by rho is n e square tau by m, right? So we can easily find the tau, and for this we need to know what is n, right? N is carrier concentration. So carrier concentration is given by Na, Avogadro number, by atomic mass m, and then multiplied by density, right? So density is given as 8.92 into 10 to the power 3. Just a second, I have to take a call. Okay. Hello, hello. স্যার আমি 8টার দিকে কল করলে হবে? হ্যালো, হ্যালো। হ্যাঁ, অ্যাকচুয়ালি ক্লাস, হ্যাঁ ক্লাস নিচ্ছে। Okay, sorry for disruption. So m is given as 63.5. So this comes out to be around 8.46 into 10 to the power 25 meter to the power minus 3, basically in units of meter cube, per meter cube. So now we have everything to find what is tau, right? So from this expression, tau will be uh, m by rho n e square. So m is electronic mass. So 9.11 into 10 to the power minus 31 kg. Rho is given resistivity 1.73 into 10 to the power 8 in SI. And then n is the carrier concentration into electronic charge square in second. So tau is around, this will be 2.38 into 10 to the power minus 27 second. So this is one part. So what is the average time between the collisions? And this relation of conductivity, it actually comes from the Drude model of electronic conduction. Okay. Now we need to find the mobility. So for mobility, there is another relation of conductivity, which is n e mu. Okay, so mu is the mobility of charge carriers, and it represents the how much mobile the electrons are. So if mobility is high, then the velocity of electrons are also high. So mu's another definition for mu, formal definition is Vd by electric field. So if we apply electric field of amount E, so how much is the drift velocity of electrons? So this is the actual formula of mobility, and it also comes in the conductivity relation. So we have mu equal to sigma by Ne, which is 1 by rho Ne, right? So rho is given as 1.73, and then N is 8.46 into 10 to the power 25. Then electronic charge. Okay, so this is the mobility part. So if we found the answer, it will be around 4.27 into just a second. Into the power minus 16 SI unit. So this is the mobility part. So everybody understood the concept. So it actually comes from the Dude model. Dude model contains both the information. So this is also another formula. This is also part of Dude model. Sigma equal to n e mu or sigma equal to n e square tau by m. Okay. So next problem. And by the way, before going to this, matlab, uh, further problem on this conductivity relation. So there is a small proof of these things. So let me prove it actually. It will not take much time. So today model can actually come from. So this has a bit longer proof n e square tau by m. But let's prove this sigma equal to mu n e. And for this, let's consider a cylindrical conductor of length L and apply electric field along this direction. So when you apply electric field along this direction, the electrons will move in the opposite direction, right? And as a result, and we also assume that there is n number of electrons per unit volume. So n is the basically carrier concentration. So so total number of electrons, if n becomes the carrier concentration, then total number of electrons or uh, the charge actually per unit volume. So this is total charge per unit volume, right? So n equal to n cube. Now let's assume this cross sectional area is A. So A is cross sectional area and L is the length. So total charge in this cylinder. So total charge in this cylinder will be what? Carrier concentration N into charge. So this becomes the total charge per unit volume and just multiply by the volume, right? A into L. So this becomes the total charge. Now what will be the total current then? Total current I becomes total charge by time, right? So NQAL by T, let's say. Now assume that drift velocity or velocity with which electrons are moving is Vd. So if L is the length, then what will be the time? So time for traversing the length L will be L by Vd, right? So here L into Vd. This means it will be NQA Vd, or simply V, velocity. And we have fundamental relation J, which is current density. So current which passes per unit area. Current density J equal to sigma into electric field applied, right? So this is total current. So current density will be total current by area, because this is per unit area. Okay. So J equal to I by A means NQA Vd by A. So NQ Vd, right? So this is J. Now this is also equal to sigma E. So if we focus on these two equation or these two equality, then what will we get? Sigma equal to NQ Vd by E, NQ mu, and where we have defined mu equal to drift velocity per unit electric field. So this is the proof. So mu is Vd by E. Now let's move to the next problem based on this. So okay, so this is for one type of charge carrier. Now let's consider a conductor where electrons also carry and holes also carry the current. So then sigma total will be n electric, for electron it is electronic charge, and electron concentration Ne, then mu mobility for electrons, and then Np for positive holes, and then charge of holes, let's say this is also electronic charge but mod of electronic charge, and mu of P. This will be total conductivity. Next problem. (1.54 into 10 to the power minus 8 SI unit at room temperature). 1 volt per meter, sorry, centimeter actually. Drift velocity electrons per meter cube. Okay, so the problem is a uniform silver wire has a resistivity of 1.54 into 10 to the power minus 8 at room temperature. Now in this case we have given the electric field, and we need to find the average drift velocity of electrons, given that the carrier concentration is 5.8 into 10 to the power 28 per meter cube, and also we need to calculate the mobility. So just calculate. So whatever I discussed here, this in this part will be used. So basically this equation may be used, this equation, and sometimes this equation as well. And of course for Dude part there is this equation. So this four equations. Let me know if any of you found the answer. Okay, so nobody found the answer. So we have given rho resistivity equal to 1.54 54 into 10 to the power minus SI unit. Then there is electric field on volt per semi, which will be 100 volt per meter, and also drift velocity is, or sorry, not drift velocity, concentration is given. Electron density or carrier concentration is 5.8 into 10 to the power 28 per meter cube. And first we need to find the average drift velocity, right? Also the mobility. So drift velocity is mu into electric field, mobility into electric field. Now mobility we do not know, but electric field we know. So we have another relation which is sigma equal to 1 by rho equal to n e mu. So rho we know, n is given, electronic charge we know, so we can extract the mu, right? So then mu is 1 by rho n e. 1.54 into 10 to the power minus 8 into 5.8 into 10 to the power 28, and then electronic charge. So mu comes out to be 6.99 minus 3 SI unit. So this is one part, right? Now if we know the mu, then drift velocity just multiplied by electric field into electric field is 100 SI unit. So this is 0.699 meter per second. Okay, so this is the drift velocity. Okay, so next problem. Okay, so this is a fairly big problem, but at least two, three problem is there. So the resistivity of a piece of silver at room temperature is given by this 1.6 into 10 to the power minus 8 SI unit, and the effective number of conduction electron is zero point 0.9 per atom. Okay, and the Fermi energy is 5.5 eV. Estimate the mean free path of the conduction electrons and calculate the electronic relaxation time, which is basically tau. Relaxation time means, and also the electrons drift velocity. So three things we need to find. Number one is lambda, mean free path, electronic relaxation time or time between two collisions, and drift velocity. So what is lambda? Lambda is basically so let's say at this time there was a collision at t equal to 0 and t equal to t prime there is another collision. So between two consecutive collision, what was the path that the electron traversed? This is mean free path. Mean free path. Okay. So these are the three things we need to find. And we have given the density 1.05 into 10 to the power 4 SI unit, and electronic mass is equivalent to the effective mass. This expression means effective mass is actually equal to the electronic mass. Okay, so another information is given, atomic weight, right? Atomic weight for silver is 107.9. So at least we can find the drift velocity and uh, relaxation time. So let's try to find it. Anyone found any of these answers? Okay, let me solve it. So we have rho equal to then electric field 100 volt per meter, and this SI unit is ohm meter. So we need tau Vd first, and then we'll determine the mean free path. Let's write down all those equations what we have or what we need to find. It will help us to uh, okay. So we have n e squared tau by m, and given m is basically me. This is one relation. Then there is another relation, n e mu mobility, but there is no mention in the mobility, although we need to find drift velocity. So Vd is mobility into electric field. And is there any other equation? So J equal to sigma E, right? So these are the mainly four equations we will use. So if we focus on tau, then we need n. So we have rho, so we can find sigma equal to 1 by rho, right? And which is equal to n square tau by m. So m we know, E also we know, so we need to find n. So n is the carrier concentration. So again it will be Na Avogadro number into density by atomic weight Ma, let's say. So it will be density is 1.05 into 10 to the power 4 by atomic mass is 107.9. So density becomes 25 meter per meter cube. So then tau we can find from this relation. Tau is m by n square rho. So n is 5.86 into 10 to the power 25, and then resistivity. Resistivity is given as 1.6 into 10 to the power minus 8 second. So tau we will have, so this will be the relaxation time or time between two consecutive collisions. Okay, and now we need to find two more things: drift velocity and mean free path. So if we use these two equation, then what happens? sigma equal to n e vd by e, right? And this is 1 by rho. From this we can find the drift velocity. Electric field is also given. So 1 by rho equal to n e vt by e, right? Drift velocity becomes 100 by rho is 1.6 into carrier concentration into electronic charge. So if we use this, then Vd will be around 0.66 into 10 to the power 2 meter per second. So what we have essentially got, let's say this was the starting point of the collision. So electron collides with this one, and then the electron goes at this point, right? So with velocity Vd, and the time between two consecutive collision is tau. So mean free path is defined as this path, the path an electron traverses between two consecutive collisions. So lambda will be simply Vd into the relaxation time. Okay, so this will be the answer we need to find. This is not given. So this will be 2.5 into 10 to the power minus 9. That is 2.5 nanometer. This will be mean free path. Okay. So next problem. So if you don't understand any of these concepts, please let me know. And you are also supposed to ask the concept which you essentially don't understand in the class. So lectures are being uploaded. So this is a very simple problem. So, evaluate the Fermi function for energy kT above the Fermi energy. Okay, so Fermi function we know. So let me write it down. So we need to find this value of this function for energy kVt above the Fermi energy. Just find it out. So anyone found the answer? So you have given energy which is, so energy is given as kBt above the Fermi energy. That means E minus EF will be kBt, right? Only then E will be kBt plus EF. So at this energy, F of E will be basically E minus EF equal to kBt. So 1 plus E uh, kBt by kBt from this expression. 1 by 1 plus E. And this will be 0.2689. This is the answer. Okay. Next problem, again very small problem. So Fermi temperature of a metal is 24,600 Kelvin. We need to calculate the Fermi velocity. So any idea how do we solve this problem? So we need to find velocity, Fermi velocity we need to find, and given Fermi temperature equal to K. So Fermi temperature is defined as Fermi energy equal to Boltzmann constant into Fermi temperature. This Fermi energy can also be written as half into m Fermi velocity square, right? So Fermi velocity equal to 2 kbTF by m root. So 2 into Fermi temperature, m is electronic mass. So the answer will be what? Need to find the velocity will be 8.63 into 10 to the power 5 meter per second. Okay. Okay. So next problem. So the thermal and electrical conductivities for copper at 20 degrees Celsius are given as 380 watt meter inverse Kelvin inverse and 5.67 into 10 to the power minus 7 ohm inverse meter inverse. Now we need to calculate the ratio of thermal and electrical conductivity. This is question 1. And then also the Lorentz number. This is just the calculation, right? The derivation, thermal and electrical conductivity ratio. But from that we need to find the Lorentz number. So what is Lorentz number? So using Sommerfeld model, we can prove that this is thermal conductivity and electrical conductivity. The ratio of these two is some number into temperature. Okay, and this temperature is in Kelvin. And for most of the metals, this actually obeys very well. So L is some constant which is purely material dependent, and this is called Lorentz number. So let's try to find this out. So if you are solving, then please post the answer in the chat box. So yeah, I have to check. I don't have answers. Okay, so the ratio is, so first ratio K by sigma is G80 by so it will be so what are the answers? So the answer is 6.7 into 10 to the power 10 to the power 8. Okay, so this is the ratio. Now the second part is Lorentz number. So Lorentz number is K by sigma T, right? So ratio by T. Now 6.70 into 10 to the power 8 by 273 plus 20 Kelvin temperature. This will be 10 to the power 6 Lorentz number. Okay, so this problem that I have
Sir,
given.
I think answer will be 2.286, 6.70 into 10 to the power of 8 dividing 293, sir.
This will be the Lorentz number, right? This is the Lorentz number.
Yes, sir.
Mm-hmm.
Yeah, that means answer will be 2.286, sir. 1 second, are you check?
2.28. Okay.
Approximately 300 means the 600 no 2 point something like that.
But there is 10 to the power 8, right?
Yes, sir.
Hmm. Okay, so before that, let me tell you one thing. So here, this is not -7. This will be +7 actually. While the concept of this problem is okay, but this will be +7. That means here will be plus. So we need to re-evaluate. So this will just be 6.70 into 10 to the power minus 6. This is number 1. So if this is -6, then now the answer will be 2.29 into 10 to the power minus 8. Okay.
Yes, sir. Yes, sir.
Mm-hmm. Yeah, but my question was also wrong, right? Here I had this -7, but the process was okay. Okay, so next problem. So we need to find the velocity of copper wire whose cross sectional area is 1 millimeter square and the current is given as 10 ampere. So and also the density of electron or the carrier concentration is given as n equal to SI unit or the per meter cube basically. So find the drift velocity. Okay, in the previous question I have not written the okay ratio unit of that ratio, right? So unit of K will be watt meter inverse Kelvin inverse, and then sigma unit will be ohm inverse meter inverse, and then there is a Kelvin for temperature, right? So this will be watt ohm and Kelvin power minus 2. So this will be unit for L. Now for this ratio, just leave the K part. This will be the unit for here, kappa K by sigma. So what will be the drift velocity for this question? We have current I equal to 10 ampere and cross sectional area on millimeter square. It will be around 10 to the power minus 6 meter square. And what is given in this one? So anyone found? Okay. So we know J equal to sigma E, where J is current by cross sectional area. So and also it will be J equal to, if we use the expression of N E mu, right? E. then it will be NEVD, because mu equal to drift velocity by electric field. So J we can evaluate VD J by NE, I by A, NE, right? So the current is 10 ampere. Cross sectional area is 10 to the power minus 6 meter square, and N is given as 8.5 SI unit, and then electronic charge. This will be meter per second. So the answer is 7.35 into 10 to the power minus 4. So this will be the drift velocity. Okay, so 11th problem. So a potential difference of 10 volt is applied longitudinally to a rectangular specimen. So, sorry. So this is suppose the rectangular length is 25 millimeter, thickness is 1.5, and then width, this one is 4 millimeter, and electric field is applied longitudinally. That means along this direction electric field is applied. So we need to find drift velocity for both electrons, v electrons and v holes, Vp. We have a very simple equation. So mu electric field. So just apply this equation and find out the drift velocity. Okay, so let me solve the problem. So what will be the electric field? We have given the voltage, right? So you all know vector equation of electric field is minus dv dr, right? So the value of electric field is voltage by the length along electric field is applied. So in this case, this is the length because electric field applied along the longitudinal direction. So 10 volt by 25 into 10 to the power minus 3 meter, right? Volt per meter. So let's keep it. So then V electron will be mu electron electric field. So mu electron is 0.38. So V electron will be 152 meter per second. Similarly, V holes will be mu P by into electric field, which is 0.18 into 10 by 25 into 10 to the power minus 3, and this will come as 72 meter per second. Okay, so these are the two answers. Now there can be another question related to this. Find intrinsic conductivity, means sigma, I'm not writing, of germanium given carrier concentration is 2.5 into 10 to the power 9 per meter cube, right? So this find intrinsic sigma. So intrinsic means the number of holes and number of electrons are same. Germanium is a semiconductor, so we usually dope the semiconductor to increase its conductivity. But intrinsic ones are those materials which have equal number of holes and electrons. So the total conductivity will be n e mu electron plus n e mu holes. Now this n are same here because it is intrinsic, so concentrations are same basically, right? So n and charge are also same. So n is given as 9 into 1.6 into 10 to the power minus 19 into mu electron is 0.38 plus 1.8, right? So this will be 2.24 ohm inverse meter inverse. So this will be intrinsic conductivity. Okay, so let's end today's session here. Next, we'll solve some problems on magnetic properties of solids and thermal. There will be more problems on the thermal properties. Few problems basically. So thank you for joining. I'm ending the meeting.